In problem 1, Ashley, Lexi, Marie, and Pilar decide to go on a hike and make some hot chocolate. So in part A, we are asking how long the component, in this case the pot, should be kept in the furnace for the mass concentration of carbon, 0.6 millimeters below the surface, to reach 1%. You can assume that the carbon can be modeled as a semi-infinite system. The properties are listed found from table 14.2. The equations are also listed, and once the properties were plugged in, a time of 17.36 seconds was calculated. This is an example of the learning objective, transient mass transfer, 6b. So in part B, a lid was put on the pot to speed up the process, and assuming that the lid is acting as a flat plate, we want to know the hydrodynamic boundary layer thickness of the air flowing above the pot. This is an example of external force convection, and here the properties are listed. You find the critical x value, plug that into the Reynolds number, and therefore you use the Reynolds number to find the final number of 0.0081 meters for the hydrodynamic boundary layer thickness. In part C, we want to calculate the rate of heat transfer to the water if the inner surface of the pot is to be maintained at 115 degrees Celsius. This is an example of the learning objective, boiling and or condensation, 7D. So here, we are assuming Q nucleate and that T set of the water is at 100 degrees Celsius. The properties are listed, and using these numerous properties, Q nucleate is calculated and then multiplied by the surface area, reaching a final answer of 13,404.58 watts. In part D, we are determining the hydrodynamic and thermal entry lengths for the hot chocolate. Approximating hot chocolate properties are the same as water through a straw, given a mass flow rate and temperature. And this is an example of internal forced convection. So for part D, the equations are listed, the Reynolds number, and then you use this to find LH and LT of a final value of 1.16 meters and 4.13 meters, respectively. In part E, we are trying to find the rate of heat loss from the side surfaces of the pot by natural convection and radiation, assuming the sides of the pot are like a flat plate. So this is natural convection, radiation, and Cartesian coordinates learning objectives. And now for the natural convection part, you find the Rayleigh and the Grashof number, plug this into the Nusselt number to get H, the heat transfer coefficient, to find Q. And then for the radiation aspect, Q rate equation is given, and you just plug in the properties to reach a final answer of 61.44 watts. That brings us to problem 2, where Ashley is baking chocolate chip cookies to bring to Marie's mermaid-themed birthday party. And she couldn't tell if they were done after 15 minutes, but joke's on her, they were only supposed to be in there for 7 minutes, so we'll see how this turns out. You can approximate the cookie as a short cylinder. So here you have to find the Biot number and tau for both a wall and a cylinder. Once you find these, you can plug them into equation 3 and 4 listed below and multiply those together. Using that, you can solve for the temperature at the inner center of the cookie, and you get a final answer of 177.76 degrees Celsius, which is way too hot for cookies, and they're definitely burnt and will be thrown away. Next, the final problem, problem 3. Cooling water is from Clear Creek and is used to condense steam in the Coors factory at a temperature of 28 degrees Celsius. We know temperature hot in and out, temperature cold in and out, the overall heat transfer coefficient and the surface area, and we're finding the mass flow rate of water needed and the rate of condensation of steam. So the equations are given to find the log mean temperature that you can then use to find Q, and then the mass of cooling water and the mass of steam. Equations there listed 5 and 6. So once you plug in the values for those, you get mass cooling water of 25.96 kilograms per second and a mass of steam of 0.313 kilograms per second.